So I understand things went well at the ball game. Today we're going to start with another kind of scattering. So the plan for today is that I want to finish this discussion of Fokker-Planck equation in pitch angle scattering that we just barely had time to start on Tuesday, and then I want to apply it to deriving the sort of canonical spectrum for diffusive shock acceleration, because I understand, I had planned to do it anyway, I understand it was advertised that I would do that. And then we're going to switch to slides and talk about how we go from this kinetic picture to a fluid picture and how we might go about incorporating it into models, primarily models of galactic winds. And I'll try to convince you at the beginning of that discussion that it really does matter how we treat the cosmic rays. Okay, so I wrote down some of what we need for brevity. Oh, and again, if you have questions at any point, please interrupt me. Okay, so we had defined this pitch angle, the cosine of the pitch angle, mu, and we were interested in the evolution of the distribution function as a function of mu and time, suppressing dependence on anything else. And we had defined this probability function, so sorry about the two p's, which is the probability that a particle with pitch angle cosine mu will experience fluctuation delta mu in a certain time. And I'd like to define these moments or averages of that probability distribution, which are going to show up later. So the mean rate of change of mu with time is we just, so C was this normalization, we just integrate delta mu over P and divide by T. So you might think that for a completely random process this should be 0. And then we have a second moment, which we define like this. And then I think last time we had got up to the point of agreeing that f at time t plus delta t would be the probability that at time t, particles with mu minus delta mu would experience a scattering of delta mu that would take them over to mu. Okay, so that was, that we sort of argued that heuristically. And then, so we didn't really get a chance to do this, we Taylor expand both sides of this equation. We Taylor expand the left-hand side with respect to time, and we Taylor expand the right-hand side with respect to mu. So we take this fp here and we write it as fp of mu, f of mu and p of mu minus delta mu d by d mu, blah. And then we divide by delta t, and we take the derivatives of mu outside the integrals, and we write things in terms of these moments. Okay, is everybody, so this is just kind of a sketch. This should all be online. Is everybody relatively happy with this? Okay, good. So now, we can unpack these derivatives, and I didn't write them all out on the board, but just using the chain rule, we can expand everything, and you can see that there'll be some terms that involve second derivatives of f, first derivatives of f, and no derivatives of f. So just letting the d by d mu's hitting the delta mu's and the delta mu's. Now, if we think that this scattering process should preserve isotropy, that is, that if f is isotropic to begin with, independent of mu, it should remain that way, then we would require that those undifferentiated terms vanish. We don't have to assume that, but we generally do. And as we'll see later on, for an actual physical model of the scattering, that turns out to be true. And so, assuming that, we have a condition that P does preserve isotropy, and that's this relationship between the second moment and the first moment. Okay, so if we assume that, then we can write this in a much more compact form. Until it's late in the week. So we just get a simple diffusion equation of the form partial f partial t is d by d mu delta mu over 2 delta t df du. Okay, so what we found is that this pitch angle scattering, if we make these assumptions, this pitch angle scattering leads to a diffusion in mu space. Okay, so this is all good, but we're going to rewrite it, and then we're going to go from that to a spatial diffusion coefficient, which is more what we're interested in. So you can see from this that delta mu over delta t is related to a scattering time. And if we do things sort of appropriately in cylindrical coordinates, and again, this will come naturally out of a more physical theory, then we can just rewrite this as d by d mu, a scattering frequency, nu, times 1 minus mu squared over 2 df d mu. And we'll see this again when we talk about waves. Okay, so this is the effect of pitch angle scattering. And so now let's, any questions about this procedure so far? Okay. So now let's consider the whole Vlasov equation for f, including the scattering term. So I think you've seen this before. Let's do things in one dimension. Let our spatial dimension be z. So the time derivative, and then the z derivative, mu v, partial f, partial z, and then there's some kind of background magnetic field that acts on these particles. So we have to include that. Q. We don't actually have an E, we just have V cross B over C dot grad P F equals our scattering term. D by d mu, nu times 1 minus mu squared df d mu. And I should say explicitly so we have one spatial dimension, and that's the direction along the magnetic field. So let's let B equals z hat B. Okay. Now, you can convince yourself as an exercise that if f is independent of gyrophase, that this term zeroes out. Okay. So there's no, okay, I see frowns. Should we show this? Okay, you're being very stoic. So I'm going to assume that you can derive it for yourselves, but if you want to ask me a question about it, we can answer that. Okay, so that simplifies the equation. And now we're going to solve this by a sort of perturbation approach. So there are 3 time scales in this equation. So one time scale is the scattering time. 1 over nu. And another time scale would be sort of an advective time. So if we assume that things vary over some length scale L, and this v here is basically the speed of light, then we have a sort of advective time L over c, and then finally we have an evolution time, which I'll just write for the time being as tau. And we're going to make the assumption, we're going to assume that the scattering is the fastest time, that the advective time is an intermediate time, and that the evolution time is the slowest time. So we're going to assume nu inverse is much less than L over c, which is much less than tau. Okay, so if we do that, then we can kind of solve this equation order by order, and we can say, well, this nu is so huge that f has to be virtually independent of mu. So our first approximation, we'll write it as Vf naught d mu, is identically 0. So to lowest order, f is isotropic, and we actually know that this is true for cosmic rays at the Earth. They're isotropic to about 1 part in 10 to the 4. So this is pretty good. So now let's advance to the next order and still neglect the evolution but keep the advection in, and then that will tell us that mu v partial f naught partial z, the isotropic part of the distribution function, is equal to d by d mu, nu, our fast scattering frequency, 1 minus mu squared df1 by d mu. Okay, so now we're relating the anisotropy to the gradient. And we can actually solve this equation if we integrate from mu to 1, and if we do that, we find that df1 by d mu is minus v over nu df naught by dz. So now we have an explicit relationship between the anisotropy and the gradient. And this just makes sense. This says, what does this say? So suppose the cosmic ray density is higher on the left and lower on the right, then there are more particles going to the left than there are to the right. Okay? So there's that anisotropy. That's really all this is saying. But now let's continue and include the evolution time. And average over mu, and we get df dt is d by dz v squared over 3 nu df dz. Okay, so now we have a spatial diffusion. This represents diffusion up and down the magnetic field lines due to pitch angle scattering. Does this all make sense? Okay. So we'll say more. So right now we have no physical model for what nu is. It's just related to angle bracket delta mu over delta t. We will develop a physical model for it when we talk about waves. For right now, let's just ignore how it's determined and switch to the shock acceleration problem. Okay, so we're going to call this D. And now we're going to we're going to mentally reorient and switch to diffusive shock acceleration. Diffusive. Okay, which we're going to call DSA. So diffusive shock acceleration is one of those ideas that was, sort of lurking in the background for many, many years, and then it just kind of burst into prominence in the late 1970s. And there were two papers published at virtually the same time that got at the same result by very different ways. The method I'm going to take you through is what's in the paper by Roger Blanford and Jerry Oestreicher in 1978. Their sort of first attempt at diffusive shock acceleration. But at the same time, a graduate student named Tony Bell did it for his thesis, a remarkably impactful thesis. There can be such a thing, that went through probability arguments and derived the same results. So we're going to do diffusive shock acceleration by the Blanford-Oestreicher method. So why did I settle on this method? I settled on this method because it uses methods that we need to talk about later to do cosmic ray hydrodynamics. The other method is just as good. Okay, so we're going to, in order to do this, we're going to make kind of a leap of faith, but try to justify it. Well, okay, let's draw a shock first. So we're going to sit in the frame of the shock, and fluid will be flowing into the shock with some velocity u1 and out at velocity u2, and we're going to assume that there's a magnetic field which is more or less perpendicular to the shock interface, and we're going to just treat this as a discontinuity. We're not going to try to resolve the structure of the shock at all, which is limited, but that's the way to start. And u1 and u2 are related by the compression ratio for the shock. So just to define that, if we write rho 2, the post-shock gas, is a number r times rho 1, then u2 over u1 is 1 over r. So there's a conserved mass flux through the shock. Okay. So the physical picture now, I think I can do one more thing. So the physical picture is that on these magnetic field lines, there are waves and fluctuations that are being carried along with the fluid. So the fluid speed is, except for the speed of light, is the biggest speed in the problem. And so a cosmic ray that, say, starts over here, crosses upstream, reflects off this wave, and comes back and reflects again. So let's think about this in the context of Fermi acceleration. Here it has a head-on collision, and it has a positive energy gain. Delta E is 2 p dot u1. And here it has an overtaking collision, so it loses some energy. So delta E is minus 2 p dot u2. But in contrast to second order Fermi, where u1 equals u2, here u2 is less than u1. And so there's a net gain per loop. And so this is a faster acceleration method than the one that Fermi originally proposed. Now, how do we quantify this? So in order to quantify this, we're going to, let me write it down and then justify it. We're going to let our cosmic ray transport equation be this, plus u df dz. Let me make sure I have the sign right here. Good, okay. Minus p over 3, so now p is, we're going back to using p for momentum. The divergence of u, which is just du dz in this context, df dp is d by dz d df dz. Okay, so there are a couple of important differences between this equation and the equation we wrote down a few minutes ago. So before we used a v for the particle speed, but here u is the fluid speed. So we're assuming that the particles are advected with the fluid. So that's this term here, and that they undergo compression. So you can convince yourself, but I'm not going to take the time to do it now. So if you want to develop some feeling for whether this equation is reasonable, you can do a couple things. One is you can integrate over p space, over momentum space, and what do you think you'll get if you integrate over momentum space? Just guess. I'm hoping you did something about the relationship between kinetics and fluids. So this is an equation for the particle distribution in phase space, and if we integrate over momentum, we'll get an equation for the particle distribution in real space, and any thought as to what that equation might be. It's the equation of continuity. So if we just define the cosmic ray density to be F d3p, then what we will get, and you can verify that for yourselves, is that partial n cosmic ray partial t is minus the divergence of u and cosmic ray. Or in this particular case, minus d by dz of u and cosmic ray. So it'll just be a reasonable fluid equation for one-dimensional flow. So that's one thing you can do. And the other sanity check that you can do, did you all get what R is? Yes. You can multiply by Cp over 3, and if you do that, you will get the pressure equation for a gamma equals 4/3 gas. So you'll find that this is the equation that describes a relativistic adiabatic gas. Okay, so any questions about these things? So I actually go through the derivation in the notes. Okay, so getting back to the shock problem. We're going to assume a steady state. So d by dt is 0. And we're going to replace du by dz by a delta function, u2 minus u1 over times delta of z. So again, that's just idealizing the shock as an infinitesimally thin layer. And then we will solve the equation in the two uniform regions. So u df dz is d by dz d df dz in regions 1 and 2. And what we'll find, so here's our shock. Let me just draw it like so. So we have fluid coming in, fluid going out, and the cosmic ray distribution on this side of the shock is going to spatially tail away in a layer of characteristic thickness L is d over u1. So that'll be kind of the exponential tail off. And here we'll have f being a constant. And we will apply jump conditions. And I will apply a jump condition to this talk because I want to get to my slides. So I will skip the details. They're in the notes. So let's just jump across a certain amount of algebra and find that F2 in the downstream region of P is proportional to P to the minus 3r over r minus 1. Sorry to be so quick, but I do want to get to the hydro. Okay. Okay, so what is R for a gas with gamma? For a gamma law gas, R goes to gamma plus 1 over gamma minus 1 for a high Mach number shock, U1 over CS much greater than 1. And if we take gamma equals 5/3, then R goes to 4, and this is beautiful agreement with the galactic cosmic ray spectrum. Okay, so this theory was a big hit right away, and so we see, so going back to Bada and Zwicky's original suggestion that cosmic rays come from supernovae, finding a lack of R process elements was kind of a blow, but diffusive shock acceleration provides a way to harness supernova energy while leaving the R process elements behind. So the shock goes out way ahead of the ejecta, and we can use the shock energy without actually taking very many supernova particles. Okay, so are we done? Do we have a complete theory of cosmic ray acceleration in shocks? No, we don't. What we've done so far has sort of two major sources of incompleteness. One is that there's no real shock layer, So all the stuff that's actually happening in the shock, all the details of diffusion, et cetera, those are all gone. And 2, we don't know the output. We don't know the amplitude of the spectrum. So all we know is that if you take a certain spectrum, it'll be compressed by a certain amount, but we don't know what spectrum you should start with. And going further requires these nonlinear theories or these kinetic simulations, and I think for that you're in Anatoly's hands. Okay. Should we go on? Questions about this? Okay, let's go on. Okay, so just to remind you, this is the plan that we laid out on Tuesday morning, and the idea was to go through the properties of cosmic rays. We've done that, and sort of divide them into particle picture and fluid picture. And to understand either one, we need to do diffusion, and we've already done something with diffusion. And so where we now are is we're going to be working toward models that either include self-consistent diffusion or don't, but one way or another give us a set of fluid equations that we can put into global calculations of the interstellar medium or intracluster medium anywhere we want to be. Okay, so the outcomes, so what we would like to get from any fluid theory, we'd like to know the force that the cosmic rays exert on the thermal gas. We would like to know how the cosmic rays themselves are transported. So we've talked a little bit about diffusion. We've talked a little bit about advection. We'd like to understand how energy is exchanged between the cosmic rays and the background medium. And if we think about this kind of in the context of other kinetic to fluid transitions, so the reason we're able to treat the air in this room as a fluid instead of a collection of particles is that the collisional mean free path is very short, and we appeal to thermodynamics to tell us that the gas is close to Maxwellian, blah, blah. So we want to do something analogous for cosmic rays, but the actual collisional mean free path is extremely long, so we can't rely on collisions. What we're going to rely on instead is wave-particle interactions. And instead of ideal gas thermodynamics or non-ideal gas thermodynamics that we know something about, we know in advance that the cosmic rays are not going to come to some kind of thermodynamic equilibrium because they have a power law energy distribution, not a Maxwellian. So what this is a little bit like, I think Matt Kuntz probably talked about collisionless plasmas with anisotropic distributions, so in a sense partially relaxed. And so this is going even beyond the collisionless gas that you encounter maybe in clusters of galaxies. And I'd like to also say that this original program was carried out by Heinz Volk and his collaborators in the early 1980s, and their immediate motivation was to calculate the back reaction of cosmic rays on a shock and go from that to some kind of self-consistent theory of shock acceleration that would predict the efficiency of shock acceleration. Okay, so what I'd like to do now is go through a few results on galactic winds that I hope will motivate some of the kind of grungy work that we do later on. So this is a comparison of work done by a couple students in my group. So you know Chad. Corey is an undergrad. He's at Haystack right now doing software as an REU. I hope he comes back to the bright side. But this is just a comparison of sound speeds and flow speeds in a gamma equals 5/3 gas versus a gamma equals 4/3 gas. And so if we identify the 4/3 gas with the cosmic rays, we can see that it leads to a more sustained acceleration and larger asymptotic velocity. So this is maybe our first hint that cosmic rays, if we could somehow get cosmic rays to drive a galactic wind, it might have desirable properties. So, some time ago, John Everett, a postdoc at Wisconsin, worked with us on a model for a wind from the inner Milky Way that fits the soft X-ray emission that was observed with ROSAT. So ignore the northern hemisphere, which is full of local features that kind of complicate things. Look at the southern hemisphere. There's this kind of clump of gas at a couple tens of millions of degrees. And we took the equations that had been developed originally for cosmic rays and then actually written down for galactic winds to making a model of a flow out of a galactic disk that includes cosmic ray pressure, that assumes that the cosmic rays are transported at the alphane speed relative to the fluid. We ignored diffusion. We had an argument for why it was small. And here are a couple of results. So here, I don't know, I hope this is legible. Here on the x-axis is the thermal gas pressure at the base of the wind, and here is the cosmic ray pressure at the base of the wind. So we just treated the disk as a boundary. We didn't deal with mass loading. I'll talk about that in a couple minutes. The color represents mass loss in solar masses per year. These hyperbole represent lines of constant total pressure, gas plus cosmic ray. The best fit is in here at a couple solar masses a year. And you can see that it relies, by best fit, I mean best fit to the soft X-rays, it relies on approximately equal thermal and cosmic ray pressure at the base of the wind. If there's not enough pressure of any kind, the gas just falls back, you fail to launch a wind. And if there's a huge amount of pressure, the gas just kind of comes boiling out. It never makes the transition from subsonic to supersonic the way these winds do. The cosmic rays do two things. They push on the gas with a pressure force, and they also heat the gas by a collisionless process that I'll describe in a few minutes. And these two curves show the temperature evolution in the wind, including the cosmic ray heating or neglecting it. And you can see that eventually, whatever you do, the gas temperature just starts dropping adiabatically, but the cosmic ray heating provides an important boost in temperature and kind of delays that fall off a little bit. So, so this was suggestive. We did get a good fit to the data. But recently, we've started doing simulations of galaxy formation that include cosmic ray feedback and attempting to include cosmic rays as a driver of a wind. So this is work with Mateusz Rostkowski, Karen Yang, done using the flash code with a cosmic ray module. I'll say more about it. And here is the gas distribution in two cases. Here, there's a toroidal magnetic field in the galaxy. There's star formation, but there are no cosmic rays. And when you add cosmic rays, boom. Okay. So whatever we've done with cosmic rays, we've gotten this big wind going. So what kind of wind you get, and if you get a wind at all, actually turns out to be kind of sensitive to how you treat the cosmic rays. So we didn't know a priori. So there are a lot of parameters going on here, and let me take you through this plot. So up here is mass loading. So this is how much, so a model only shows up in this upper row if it drives a wind at all, and this is time, and this is the amount of mass that's loaded into the wind. So here a lot, here a little. And then down here is the star formation rate in solar masses per year, and the time goes out to 500 million years. Okay, so there are a lot of parameters going on here. So the parameter f parameterizes the efficiency of cosmic ray streaming. I'll explain it a little bit later. Supernova feedback efficiency is just our recipe. So we have a recipe for star formation that has a lot in common with other people's recipes, and we just say for every 100 solar masses of stars that are formed, you get one supernova, or for every 185 solar masses, you get one supernova. So this is something that can be dialed up and down, and it's just an input parameter. And then this F sub CR is the fraction of supernova energy that goes into cosmic rays. So 0.1 is black, 0.15 is red, 0.3 is green. Okay, then magnetic field 3 microgauss. So the left column, this F parameter is 4. Here, the F parameter is, what is it? Oh, it's 8, 4, or 1, or 0, blue. So you see if there's no streaming, you get no wind. And then there are other models with diffusion. So don't try to get all these cases straight in your mind. There are a couple of things to take away. One is that up to the values that we tested, the larger this streaming parameter is, the more of a wind you drive. And 2, F has to be greater than 1 to drive any kind of wind at all. And 3, so we have a multitude of treatments to deal with, a lot of unanswered questions that are just parameterized, and it really makes a difference if you get a wind going and what kind of star formation rate you have. So I think we're very motivated to take this beyond the input parameter, order an input parameter and run the model stage. Okay, so now we're going to get back in the trenches. So we're going to consider the dynamics perpendicular to the magnetic field and parallel to the magnetic field. Okay, so the perpendicular dynamics are kind of easy. So perpendicular to the magnetic field, the cosmic rays have a current, and the perpendicular gradient of the pressure balances the Lorentz force on the cosmic rays. Don't worry, we're not going to actually compute the cosmic ray current. And the gas has a current Jg, and that contributes a Lorentz force. So if we add, if we write the Lorentz force on the thermal gas in terms of the total current minus the cosmic ray current, then we can substitute for, there should be a thermal gas pressure here too, but basically the cosmic rays contribute a perpendicular gas pressure gradient force through their current. So we can use Ampere's law, eliminate the current altogether, and we never have to talk about what the individual currents in either species are. We just know that J cross B is curl B cross B. Okay, so for dynamics perpendicular to the magnetic field, we can just add the cosmic ray pressure gradient to the gas pressure gradient. The parallel dynamics are trickier, but the basic idea, the gist of it, is that the cosmic rays are well scattered, and the scattering transfers momentum and energy. So there's momentum and energy transfer between the cosmic rays and the thermal gas mediated by the magnetic field. Okay, so let's talk a little bit about waves and how we work out the relationship between the cosmic rays and the waves. So of course this isn't a real digression because we need it. So let's consider a wave with electric field E1 and magnetic field B1, and it has a K and omega dependence like this. And from Faraday's law, there's a relationship between B1 and E1, so we'll be able to eliminate B1 in favor of E1. So what we do is for every species in the plasma, alpha, we solve a linearized Vlasov equation for that species. So we calculate the perturbation to the distribution function that arises from the wave fields acting on the zero-order distribution function. You've probably seen this before, right? Yes, okay. And then once we have F, the perturbation to the distribution function, we compute the current density, so J1 for every species, by just taking the velocity moment with F1, and I've written J1 and F1 as functions of E1, just to remind you that they are. And then if we put this into Ampere's law and use Faraday's law, again, we get a dispersion relation for E1, where this quantity, so in a vacuum, this would just reduce to omega squared equals c squared k squared. But here we have the contributions to the current from all the species. So this will give us the dispersion properties of the wave. And so the kinds of macroscopic waves that we have in a magnetized fluid would be the alphane and magnetosonic waves, and you can derive those from fluid equations. And if you put in things like resistivity and viscosity and thermal conduction, you'll find typically dissipation of those waves. But if you do it collisionally like this, you find other forms of dissipation, Landau damping, gyroresonant damping. And so this is kind of a general approach. And what we will do to include the cosmic rays, so we'll talk about this in kind of in two parts. So if you read chapter 12 of Russell Culsred's book, you know something about the cosmic ray streaming instability. And the standard treatment is to evaluate that dispersion relation that I showed on the previous slide, including thermal electrons, thermal ions, and cosmic ray ions. So typically just one species of cosmic rays. And keep only the gyroresonant cosmic ray distribution. So the justification for doing that is that in the interstellar medium, cosmic rays are only one particle in a billion, so they don't really contribute a whole lot to the current, but they're important for their ability to excite or damp waves. So later on, we're going to discuss a more general treatment, which is appropriate when the flux of cosmic rays is high, and we'll talk about high compared to what. And in that case, you keep the entire cosmic ray distribution, and if there are enough cosmic rays, you also want to balance the equilibrium cosmic ray current by putting in some thermal electrons, and this will lead to the non-resonant instabilities that I think Anatoly talked about yesterday. Okay, so that's the program. And after some work, this is what we find for the gyroresonant streaming instability of cosmic rays. So we're going to write the growth rate as capital gamma sub cosmic ray. And what is it? Well, so it's this integral over momentum space. F here is the unperturbed cosmic ray distribution. And we can identify, and the sum here is not over species, but over polarization states. So we can consider left and circularly polarized waves. And so here is a resonance condition. This is what we talked about last time for gyroresonance. So when this is 0, this says that the Doppler shifted frequency that a cosmic ray sees as it moves down the field line is equal to plus or minus the gyro frequency of that cosmic ray, okay? And mu is the pitch angle, v is the velocity, and then F appears here in two terms. So this term, dF dP, is negative for a power law, and it represents damping. And it's generally negative for a thermal distribution, too. So if there's any instability here, any excitation of this wave, it comes about through this velocity space anisotropy. And notice that the anisotropy term is multiplied by kv over omega. So v is like the speed of light, and if we have an alphane wave, then omega over k is like the alphane speed. So kV over omega is of order 10 to the 4 in the interstellar medium. And what that means is that even a tiny anisotropy can overwhelm the damping due to the power law dependence. So fortunately, we don't have to evaluate this every time we want to talk about the streaming instability, because there's a simple approximation to the growth rate that's very useful, and that's written here. So there's a constant c, which depends on the spectrum, and it's of order 1. Omega Ci is the proton, actually it's the non-relativistic gyro frequency of the cosmic rays. Ni is the number density of thermal ions. N cosmic ray greater than P1 is the number of cosmic rays that have more momentum than a certain minimum. And this minimum momentum, P1, is the minimum cosmic ray momentum that can resonate with a wave of a given k. So the longer the wavelength is, the smaller k is, the larger P1 is, and the smaller this number will be. So in the interstellar medium, this number is about 10 to the minus 9. And here is the drift velocity, VA, VD over VA minus 1. And let me actually write down explicitly what VD is. So VD would be the integral over momentum space of mu v f. And so if f is independent of mu, then v drift is 0. And what this growth rate formula here says is that an anisotropy that's greater than the alphane speed will lead to instability. You can verify, if you do a Lorentz transformation and use the Lorentz invariance of the distribution function, that this expression here is just df d mu in the frame of the wave. So what this says is that if the alphane wave sitting in its own rest frame sees a positive cosmic ray anisotropy, the wave will grow, will be amplified, momentum and energy will be added to it. Okay. So this streaming instability was discovered in the 1960s, and it's continuing to pay rich dividends. Okay, so now let's make contact with the scattering work that we did a few minutes ago. Okay, so what we do is we find the back reaction of the perturbed distribution function acting with the wave fields on the equilibrium distribution function. So E1 and B1 are the fields in the wave that we talked about a couple of slides back. F1 is the perturbation to the distribution function that arises from E1 and B1. And if you average over a randomly phased distribution of waves and crunch along for a while, you find that this has the form of a diffusion equation. That this shouldn't really surprise you, because if we go back to the equation for F1 in the first place, we see that it involved the momentum derivative of F0, the F0 distribution function. So F1 is going to be proportional to the gradient of F0, and that kind of motivates the fact that this eventually turns into a diffusion equation. Okay. So this diffusion equation, as we've been deriving it, is a tensor in p mu space. So p is the magnitude of the momentum, mu is the pitch angle, and the largest term in this diffusion equation is the pitch angle scattering term, d mu mu. And it corresponds to a scattering frequency that's of order the cyclotron frequency. Now this is the relativistic cyclotron frequency of the cosmic ray, times the amplitude of the wave in units of the background field squared. In the interstellar medium, this is a kind of tiny number. It's thought to be about 10 to the minus 6, but it gives enough pitch angle scattering to explain the anisotropy. The off-diagonal elements of the diffusion tensor are of order VA over C, and the DPP term itself is of order VA over C squared. What this says physically is that because Alfvén waves move very slowly compared to the speed of light, they don't really do very much to accelerate particles. So just as we found that Fermi acceleration, second order Fermi acceleration, is sort of quantitatively doomed in the galaxy because v, the speed of the magnetic clouds, is so much less than the speed of light, Alfvén waves don't do very much to change the energies of cosmic rays. They're important mostly for pitch angle scattering them. Okay, so if we just keep d mu mu and neglect all the other terms, we get back to what we had before. So what we had before was, it was just an idea without a physical model for pitch angle scattering. What we've now shown with this linear and quasi-linear Vlasov theory is that scattering from Alfvén waves is a process like what we idealized before with delta mu, delta mu. So this is nice. There's real physics behind that statistical model. So I went through this before, so we don't have to do it very much. We go to the large scattering limit. F has to be isotropic to lowest order. So we derive F1 in dF1 d mu in terms of the spatial gradient, and we derive this spatial diffusion equation. Okay, but now we have a model for what d mu mu actually is. So now let's talk about energy transfer. So if we multiply that Fokker-Planck equation by particle energy and integrate over momentum space, we get a conservation law for energy of all the cosmic rays. So UC here is the cosmic ray energy density, WC is their energy flux, and what we can show from the Fokker-Planck equation is that the right-hand side of this equation is the growth rate of a given wave of frequency omega and wave number k times the energy in that wave integrated over all waves. So this is what you would want a theory to do. This says that in the absence of waves, cosmic ray energy is conserved. We haven't put in any other loss mechanisms. But if we include the waves, if the waves grow, the cosmic rays lose energy, and if the waves are damped, the cosmic rays gain energy. And I would just note that if you want to try this at home, you should use the full diffusion tensor, not just the d mu mu, which corresponds to elastic scattering. So this is, I wouldn't say that the Fokker-Planck theory proves energy conservation. I would say that Fokker-Planck theory holds up to energy conservation, which we know is physically reasonable. So as I said a minute ago, you have to include both terms in the both the d mu mu and the d mu p to get this right. And if we do this, we can actually write, so this is a reasonable equation in principle, but it's sort of nasty, and it's not really clear how to evaluate it. But if we use the relationship between the growth rate, which depends on the anisotropy, and the anisotropy and the spatial gradient, we can write this in a really nice, compact form, namely VA dot grad P cosmic ray. So the energy transfer from waves to particles winds up looking like a frictional heating. Okay, there's no physical friction in the sense of no physical collisions, but the energy transfer from cosmic rays to waves can be written as if it were a friction. So nice and compact and easy to use. Okay, so we need an evolution equation for the waves as well. And so there are some WKB terms that kind of represent swelling or rarefaction. U here is the velocity of the fluid. Then there's cosmic ray driving or dissipation, depending on which way the waves are going, and a heating rate. And so if we want the thermal balance for everything to come out right, we identify this G term, the dissipation of the waves, with an entropy gain of the gas. Okay, so we get a nice compact set of equations. What happens if you actually try to solve these equations? Well, very few people do, but we did. So this is a model, again with John Everett from a few years ago, where we said, well, what happens if you have an ionized gas with a partially neutral cloud in it? This happens all the time in the interstellar medium. What happens to cosmic rays and waves as they encounter this cloud? So this is just a schematic of what the cloud looks like. The ionization fraction is 1. Then in the thin transition region, it drops to 10 to the minus 3. The gas temperature goes from hot to cold, and the gas density goes from low to high in a way that preserves total pressure. And so if you solve the cosmic ray and wave equations together, this is what happens. The cosmic ray pressure stays almost constant. The wave pressure goes from a low value to a little skin where there's a very high value. And this is associated with the transition from cosmic rays being locked to the waves finding it very hard to survive due to ion-neutral friction. So you get this little thin skin, and then and remember, since the scattering rate is proportional to wave intensity and the diffusion rate is inversely proportional to the scattering intensity, the diffusion coefficient goes way down as the wave pressure goes up, and then the whole diffusion approximation breaks down, and the cosmic rays just stream freely into the cloud. So in principle, this is a complete model that you can solve. And so this pretty much is this classical hydrodynamics, classical cosmic ray hydrodynamics that forms the basis for wind models and other models for the impact of cosmic rays on shocks and on the interstellar medium. So they stream down their pressure gradient at the Alfvén speed relative to the thermal gas. I'll say a little bit about how you implement this. They transfer momentum through their pressure gradient. They heat the gas at this VA.grad P cosmic ray rate. And there's also a little bit of diffusion. Kappa is V squared over nu. And this has been applied to shocks, to galactic winds, to heating the interstellar medium, and to heating the intracluster medium. Okay, so these are kind of the basic ingredients. Now, how do you actually implement the streaming? So the idea is that the cosmic rays propagate down their density gradient, and if the density gradient changes sign, the streaming should change sign too. And so if you start with, say, a sinusoidal perturbation of an otherwise constant cosmic ray density, what you would expect is that the gradient would flatten over time. So here they stream to the right, here they stream to the left, and so you would kind of tend to relax to a uniform distribution going down here and going up here. So the equation that you're sort of dragged in the direction of solving is an equation something like this, where df dt, so this is the time-dependent term, and then there's the advective term, and the advective velocity depends on the sign of the gradient of f. Okay, so a binary switch like this is very difficult to implement numerically, but Pratik Sharma, who was a grad student here, actually worked with Jim Stone, isn't that right? Yes, okay. He claimed credit. Oh, well, I thought he also worked with you, right?
He did work with me, but
yeah. So he introduced a procedure later when he was a postdoc to replace this binary switch here with a more gradual, so replace it with a hyperbolic tangent with a characteristic width of the transition of order 1 over epsilon, and using this regularized equation, we were able to implement cosmic ray streaming in Flash. This is a numerical test. So this prescription for streaming has an interesting implication, which was first pointed out by Skilling in 1971, sort of a bottleneck effect. So when the cosmic rays are perfectly locked to the waves, ignoring diffusion, there's a constant, which is their pressure times the alphane speed to the gamma cosmic ray power, so about 4/3. And what this says is that if the alphane speed is decreasing for some reason, so say as you're going into a cloud, the magnetic field is staying roughly constant, the density is going up, the alphane speed is going down, just like traffic flow, the cosmic ray pressure should go up. So that means that cosmic rays, so the cosmic rays are kind of streaming in from the left, but their pressure is actually rising. That means they're streaming up their density gradient. So, so Skilling said this should not be allowed. This should not be allowed to happen. So what will happen? What will happen in a situation like that? So what he conjectured, but didn't prove, was that the cosmic rays would settle down to a constant density kind of between their source and that bottleneck. They would be streaming at the minimum alphane speed in the system. They would kind of make their way over to the bottleneck, but there would be no waves to couple them to the gas, and there would be no gradient. So we've actually, somewhat to my surprise, been able to validate this numerically. So this is work with Josh Wiener, a postdoc in my group, and Peng O, that we're almost at the point of submitting. And the model here is we've just made a simple model cloud. So there's a density peak here, like this. And we put a source of cosmic rays over on the left, and we let them stream in. And what happens is that their profile just goes flat behind the density maximum. If we put in a continual, say a decreasing density, then we find very good agreement. The cosmic ray density decreases. The conservation law with the alphane speed is preserved. But here we just get this very slow streaming to the left of the density maximum. What happens over here, so you get this huge cosmic ray pressure gradient, and what happens is it starts pushing on the cloud and it actually erodes it. So that's a subject for another talk. Okay. So I want to say a little bit about constrained diffusion. So we saw that you can write the cosmic ray pressure gradient, the cosmic ray density gradient, in terms of the velocity space anisotropy, and that means that you can write the streaming instability growth rate in terms of the spatial gradient. But in a steady state, whatever is around to damp the waves, any dissipative effect in the medium, should balance the cosmic ray growth rate. And so what that kind of means, if you take it seriously, is that the spatial gradient of the cosmic rays is constrained. And we know of at least 3 mechanisms that damp the waves, and they're important in media with different properties. So there's ion-neutral friction, which I already mentioned. It tends to wipe out the waves in partially ionized gas. There's a process called nonlinear Landau damping, which we can kind of think of as thermal ions resonating with the global profile of a wave packet. That's important in hot gas. If the plasma beta is not too small, if it's too small, there aren't enough thermal ions that can keep up with the alphane speed. And then there's a process that was described more recently called turbulent damping, where if the waves are propagating in a medium with large-scale turbulence, they get kind of sheared out of coherence and they don't scatter the cosmic rays anymore. The upshot of all these damping processes is that this self-confinement picture where cosmic rays scatter from waves they generate themselves through the streaming instability probably only works below a couple of hundred GeV. And so the confinement of cosmic rays above this energy must be due to some other form of turbulence, which fortunately there are in the interstellar medium. Okay, so this lets us talk about that F parameter, which I'm sure you've been carrying around in your heads. So remember, F is the multiple of the alphane speed that the cosmic rays stream at, and we can compute it by balancing the wave damping and the wave growth. And what that leads to is that we can actually replace the diffusion term in the transport equation with a super-Alfvénic streaming term. Now, this could make you nervous. It made me nervous because we're taking a second-order equation, diffusion is a second-order operator, and replacing it with a first-order operator. How can we do that? Well, we're sort of allowed to do that because we have this extra constraint. So we can think of the extra constraint as reducing the order of the system. But as far as the numerical implementation, whether they're actually equivalent, that is really not well tested. And that's kind of on our list for things to do. Okay, so this just says in equation what I said in words. So how have people risen to the challenge of implementing this in, for example, cosmic ray driven galactic winds? So the easiest thing to do is just include the cosmic ray pressure gradient and assume that the cosmic rays are advected with the fluid. Ignore the heating, put in isotropic diffusion if you want, and one of the main advantages of this is that you don't actually have to calculate the magnetic field. So magnetic fields are maybe not that important in driving galactic winds. They don't account for a huge amount of energy density. So they're really just kind of along for the ride and to discipline the cosmic rays. So if you go to this other model, you can kind of cut the magnetic field out entirely. As we'll see, this actually corresponds to a physical picture, which we'll describe. Something else that's been done is to include streaming relative to the thermal gas and include some form of frictional heating, but replace the Alfvén speed by some other speed, typically the thermal sound speed. And this has the same advantages as this approach, namely that you don't have to calculate the magnetic field. And I'm going to argue that there's really not much of a physical basis for this. Okay. So to find a physical basis for these treatments, or the lack of one, let's try to generalize cosmic ray hydrodynamics. And let's do that by accounting for non-cosmic ray sources of waves. So this is, I guess, not the same, but similar to a picture that Vladimir Zhdankin showed in a few seconds last night. This is a simulation of MHD turbulence from my colleague Stas Boldyrev's group. And assuming that there is some kind of turbulence in the interstellar medium, let's generalize our Fokker-Planck equation to include waves that travel in both directions. So now we write down wave evolution equations for, so plus and minus are the directions that the waves are propagating in. So the waves are either driven or damped by the cosmic rays. They're driven externally. They have some dissipation rate. These are their energy fluxes corresponding to the direction that they're propagating in. And that allows us to define a sort of composite streaming velocity, which is the relative frequencies of the scattering by waves going in the plus direction and the minus direction. So if the scattering were due to self-confinement alone, we would only have nu plus, and then this would just be VA. But if we have equal quantities of waves going in both directions, then the streaming velocity is 0, and whatever the cosmic rays scatter off of, they do transfer momentum. If we balance driving and damping, we can make a model for what the intensities of the waves traveling in the two directions are. And it comes down to one parameter, which is kind of the ratio of driving extrinsically to driving by cosmic rays. So if the extrinsic driving is very strong, then x is very large and w goes to 0. But if the extrinsic driving is weak, then the transport velocity is just the Alfvén speed. So the cosmic ray heating is reduced when it's proportional to w, but there has to be some other form of turbulent damping, so it's not really clear how the energetics should come out. So the extrinsic turbulence model, which was the first alternative treatment that I described is self-consistent. You advect the cosmic rays at the speed of the fluid, you neglect the cosmic ray heating, you keep in the pressure gradient force. And this is a valid limit for strongly driven extrinsic turbulence. Okay. I have a couple minutes, so let me just describe a little bit of additional work that goes beyond the Alfvén wave model. So in a very high beta plasma, like probably the intracluster medium, Alfvén waves are modified by finite Larmor radius effects in the ions. And they split into two branches, and one of them, the fast mode, has a very large phase speed, and the other has a very slow phase speed, which actually asymptotes and becomes independent of wave number. And because there are these slow waves that are subject to cosmic ray driving or damping, this family of waves tends to enforce sub-Alfvénic streaming. So I would argue that in a very high beta plasma, rather than streaming at the sound speed, cosmic rays would tend to stream at a speed that's slower than the Alfvén speed. This is my conjecture, but I haven't actually been able to show it yet, or because I haven't had time. Okay. The other important advance from the streaming instability are these non-resonant instabilities, which I think Anatoly mentioned. And so this corresponds to the case of a high flux of cosmic rays that contribute actually to the whole dispersion relation. The waves that are driven by these cosmic rays are not Alfvén waves. They're much faster than Alfvén waves, and they grow very fast. And we can expect these waves to exist whenever the cosmic ray whenever the cosmic ray density over the magnetic field energy density is bigger than this number, the speed of sound over the drift speed. So in the galaxy at large, this number here is very large, and this number here is about 1. But in the vicinity of shocks, where diffusive shock acceleration is taking place, this number is smaller, and this number can become very big. So that leads to this additional class of instabilities that seem to be able to drastically modify the structure of the shock. If you add thermal effects to these non-resonant instabilities, the growth rate is reduced, but you don't kill them. So these are the resonant instabilities, these are the non-resonant instabilities, and this is by now a probably outdated PIC simulation showing how magnetic fields grow due to these non-resonant instabilities. So that's just a summary of what I said. And now let's take a minute to go back and look at where we are for cosmic ray feedback. Okay, so what do you need to do cosmic ray feedback properly at a minimum? We need a good model for the interstellar medium. And that includes its magnetic field and be able to say something about the properties of turbulence in the ISM. And you need a good model for the star formation rate. So you heard a lecture from Eve about star formation and the kind of feedback it can produce. So you have to assume all that's been worked out. And then you need to be able to go from a star formation rate to a supernova rate, and from a supernova rate to a cosmic ray acceleration rate. And that tells you the rate at which cosmic rays are being put into the medium. And then you need a model for how cosmic rays are coupled to the ambient medium under a variety of conditions. So you have your cool, weakly ionized gas, you have your hot, fully ionized gas, more or less turbulence, weaker or stronger magnetic field. And if you have all these things, you should be able to make a self-consistent model of the interstellar medium and an outflow, if it exists, that includes cosmic rays. So it'd be a wonderful reward for all that work. There would be some bonuses. You could, so what happens to the cosmic rays after they leave the disk of the galaxy? So they affect the circumgalactic medium, the intracluster medium, the intergalactic medium. They can spread magnetic fields around, and they can heat the gas. So you'd be able to calculate that as a bonus. And you'd be able to test all this against observed galactic winds. You'd be able to calculate radio and gamma ray spectra. And I showed you a little bit on Tuesday of how one can go about doing this. So this is, I think, a great time to be doing cosmic ray feedback. We should never forget that just the fact that they exist is kind of amazing. They show up everywhere, 1 particle in a billion, carrying as much energy as everything else. Even though they're collisionless, they exchange energy and momentum very freely with the background medium. And we have all these tools that are getting better all the time that are making it possible to actually calculate the effects of these things. So we're done. We have some time for questions.